Hi everyone, my name is Önder Askin from University Bochum, and in this talk I'll present new methods for estimating and auditing FDP, which is a popular variant of differential privacy. The methods presented in this talk are the result of joint work with my colleagues Holger Dette, Martin Dunsche, Tim Kutta, Yun Lu, Yu Wei, and Vassilis Zikas. Here's a brief outline of this talk. We'll start by introducing the privacy notion that we want to audit, namely f-differential privacy. We then take a look at how to estimate the privacy parameters in FDP. And finally, we will discuss how to audit privacy claims in the FDP framework. All right, let's start with our privacy notion. So here's a typical scenario in differential privacy. We have a database D, a mechanism that processes data, and an output M of D. What our mechanism usually does is to compute a statistic with information from D and combine that statistic with some random noise in order to ensure privacy. To further quantify privacy, we consider a neighboring database D dash that we can obtain from the original database D by altering the information of one and exactly one individual in the original database. We can then take a look at the output of our mechanism on these neighboring databases. And the idea of differential privacy is that the closer these two outputs are, the less any one individual in database D will have affected the output of our mechanism, which in turn means more privacy for the individuals in database D. In standard differential privacy, this notion of closeness is expressed with the help of two privacy parameters, epsilon and delta, where epsilon lies on the positive real line and delta lies on the unit interval. And if one takes a closer look at the definition of standard differential privacy, one notices that the smaller these two privacy parameters are chosen, the closer the two probability distributions attached to the output M of D and M of D dash are, and the closer these two distributions are, the less distinguishable these outputs become, and the more privacy there will be for the individuals in our database. In f-differential privacy, this notion of closeness or indistinguishability is formalized through the lens of an adversary. And that adversary will play a guessing game and will be provided with a value x that might either correspond to the output M of D or the output M of D dash. The adversary will have to decide which database produced the value x. The idea behind this guessing game is that the better the adversary can do, the less indistinguishable the outputs M of D and M of D dash are, and therefore the less privacy there will be attached to the output of mechanism M. This decision task can be expressed as a testing problem, where we have a hypothesis that indicates that the value x was produced by database D, and an alternative H1 that indicates that the value x was produced by our database D dash. The adversary can then deploy a hypothesis test to arrive at a decision that either points to the hypothesis or the alternative, and any test that the adversary might deploy will have two types of errors attached to it. The type 1 error, alpha g, which corresponds to the probability of falsely rejecting the hypothesis, and the type 2 error, beta g, which corresponds to the probability of falsely failing to reject the hypothesis. We are then naturally interested in the smallest possible combination of these two errors, and to do so we can look at a fixed type 1 error at level alpha and consider the smallest possible type 2 error for this fixed level alpha. We can arrive at this smallest possible type 2 error beta by going through all tests which have a type 1 error smaller than this alpha and choose the one test that has the smallest error among these tests. And luckily, we can do this right away because we know the optimal test in this setting, that is the likelihood ratio test. And the likelihood ratio test works in the following way. It takes the probability densities, P and Q, that are attached to the mechanism output M of D and M of D dash respectively. And it takes also constants eta and lambda where eta is a positive or non-negative threshold constant and lambda is a coin toss probability. And this optimal likelihood ratio test then rejects the hypothesis if the density quotient lies above this threshold eta. It also rejects if the density quotient equals eta and a coin toss provides us with heads, where the probability for the outcome heads is given by the coin toss probability lambda. So with the optimal test in hand, we can then compute the smallest possible combination of errors for any level alpha, and we can actually plot this collection of type 1 and type 2 errors and obtain a trade-off curve T. And this trade-off curve has some very useful information with regard to the indistinguishability of these outputs m of d and m of d dash. One important piece of information from this trade-off curve T is that no adversary will achieve a combination of type 1 and type 2 error below this curve, because any combination that lies below this curve would be better than the optimal test, the optimal likelihood ratio test, and that is not feasible. So this trade-off curve very well indicates how distinguishable these two outputs are. And this trade-off curve T is also the central object of interest in f-differential privacy. So this trade-off function T is the parameter that we will want to estimate and audit later on. And it is also central to the definition of f-differential privacy. So a mechanism M is FDP for a function f if any trade-off curve implied by two neighboring databases d and d dash lies above this function f. Alright, now that we have established our privacy notion and the privacy parameter that we want to investigate later on, we might ask ourselves why we would look at f-differential privacy in the first place. And there are a number of reasons why f-differential privacy is an interesting privacy notion. F-differential privacy comes with easily interpretable privacy guarantees. It is suitable for reasoning about the composition of algorithms and for studying privacy amplification, which are important tools when building more complex privacy-preserving systems out of differentially private building blocks. And it has become increasingly popular as a framework for auditing private machine learning. So there are a number of reasons why we are looking at this privacy notion and why we want to audit it. Alright, we now consider the task of estimating the privacy parameter in FDP. We take a look at the scenario from before, where we have a database D, a mechanism M, and that mechanism's output M of D, and we consider a black box setting where we have no knowledge of the mechanism's code or structure. We have an auditor that is tasked with estimating the privacy parameter or trade-off function of this mechanism M. And to do so, we consider the same setting that we used to define f-differential privacy in the first place. So we choose a suitable neighboring database D dash. We run our mechanism repeatedly on these neighboring databases to produce output samples x1 to xn and y1 to yn, which correspond to the outputs m of d and m of d dash respectively. And we then recall that to define the trade-off function T of mechanism M, we used the likelihood ratio test, which in turn relies on the densities associated with the output of our mechanism. Since we are in a black box scenario, we don't know these densities. However, we can use our output samples x1 to xn and y1 to yn to derive approximations of these densities, and then hopefully use these to emulate the likelihood ratio test from before. So in order to obtain these approximations, we use the kernel density estimator, which is defined with the help of a bandwidth parameter b and a kernel function k, and which can be understood as the weighted sum of density bumps around our observations and sample data x1 to xn, for instance. And we could then, now theoretically, plug these density estimators into our likelihood ratio test to obtain an approximation of the trade-off function T of our mechanism. However, it turns out that certain parts of our likelihood ratio tests are difficult to mimic in estimation. And this especially concerns the part where we decide whether to reject the hypothesis with the help of a coin toss. The reason for this is that even though our approximations of Q and P might be accurate, the ratio of our estimates itself will usually not be equal to this threshold eta. So in order to avoid this difficulty, we consider a perturbed version of our likelihood ratio test that rejects if our density quotient lies above a perturbed threshold eta plus h times u, where h corresponds to a small positive constant and u is a random variable that is uniformly drawn from the interval minus 1/2 to 1/2. This perturbed likelihood ratio test has also a trade-off function th, which happens to converge uniformly to the trade-off function t defined by the optimal likelihood ratio test. So it converges uniformly to our true trade-off function t as our parameter h goes to 0. And our hope now is that an estimate for the trade-off function th of the perturbed likelihood ratio test will also converge uniformly to the true trade-off function t. To illustrate this, we can consider an example. Here we consider the Laplace mechanism, where its trade-off function t, its true trade-off function, is given by the blue curve, and the estimate t at h is given by the red curve. We obtain this estimate with the help of the perturbed likelihood ratio test and with sample size n equals 200. Now the points of this trade-off function or our estimate for this trade-off function, THH, can be computed with the help of the formula to the right. And we observe that these points are calculated dependent on our threshold eta that we use to define our likelihood ratio test. So in practice, if we want to obtain an estimate for the entire curve, we would then compute these points for a range of eta values. An important aspect of this estimate THH is given below. It converges uniformly to the true trade-off function t as long as our sample size n grows. And we can illustrate this again with the help of our new estimate THH, which we obtain with a sample size n equals 5000. Here given by the yellow curve. And we see right away that this curve almost overlaps with the true trade-off function t, which speaks to the approximation of our estimator. We also note that sample sizes of n equals 200 and n equals 5000 are rather moderate in black box estimation. And we are therefore quite happy with the performance of our estimator THH. Okay, we now turn to auditing privacy claims in the FDP framework. To get a better understanding of this task, we first familiarize ourselves with the privacy parameters in both the standard DP setting, pictured on the right, and the FDP setting, pictured on the left. In standard DP, smaller privacy parameters will indicate more privacy. So epsilon2 will indicate more privacy than epsilon1, and a privacy parameter equal to 0 will indicate the maximum amount of privacy that can be achieved in the standard DP setting. In FDP, our privacy parameters behave a little differently. Here, larger trade-off curves will indicate more privacy. So T2 will indicate more privacy than T1, and the trade-off curve that is equal to 1 minus alpha will indicate the maximum amount of privacy that can be achieved in the FDP setting. The goal of auditing is to detect privacy violations and to expose flawed mechanism in the process. And again, to get a better understanding of what actually constitutes a privacy violation, we take a look at standard DP first, and we consider the following constellation. We have a privacy claim, epsilon0, that lies well below the privacy parameter epsilon that can actually be achieved by our privacy mechanism M. So our privacy claim is too optimistic and does not accurately reflect the amount of privacy that our mechanism can afford to individual users. And this privacy violation comes as a visible distance between the two privacy parameters. We can now consider a similar constellation in FDP, where we have a claimed privacy level T0, and the actual amount of privacy that our mechanism can achieve trade-off curve T that lies well below this privacy claim T0. We can again observe that there is a visible discrepancy between the two, and the plot to our left provides us with an idea on how to audit this privacy claim T0. We could use our estimator from before to get an estimate of the actual privacy level T and compare this estimate against the privacy claim T0 in order to see whether there is a visible discrepancy between the two, which would point to a privacy violation. To illustrate this approach, we take a look at an example. Here we have a flawed version of the Gaussian mechanism, a privacy claim T0 that is too optimistic, and an estimate for the true privacy parameter T at h. We observe a visible distance between the two trade-off functions. However, what we need is a method with which we can assign some statistical significance to the discrepancy that we observe in order to reliably reject false privacy claims. And it turns out that we can find such a method by focusing on single points on our trade-off functions. This allows us to deploy optimal classification theory, and it provides us with estimates alpha tilde and beta tilde for our points that come with confidence intervals for their expected values. This means that we can fix a confidence parameter gamma and bound the deviation of our estimates from their expected values with high probability. We can use these results to construct a confidence region that can help us to reliably reject false privacy claims. To construct this confidence region, we first identify the point where the distance between our estimate and our privacy claim is largest. We then use the confidence intervals from before to construct a confidence region around that point. And this constellation of privacy claim and confidence region already points at a privacy violation with high probability. Why is this the case? Our confidence region was designed to contain the expected values of our estimates with high probability. At the same time, these expected values can be identified as the type 1 and type 2 error of the hypothesis test that uses the underlying classifier for our estimates. Hence, these expected values should lie above our trade-off function T0. And the only way that both of these statements are true is if our confidence region overlaps with our privacy claim. This is not the case in our example, and therefore our privacy claim is probably false. So we can, with some confidence, determine that we have a flawed version of the Gaussian mechanism on our hand. We conclude this talk with a brief summary of our work. We have devised a new approach for estimating and auditing FDP in black box settings. Our methods reliably infer and detect privacy violations and come with theoretical guarantees of convergence under mild regularity assumptions. I would like to encourage you to take a closer look at our paper for more details on algorithms, theory, and experiments. And I would like to thank you for listening.